Good morning, good evening, good night, wherever you are. I'm really happy to be able to talk to you about this topic. Um, and it's an idea that falls within biocomputing. If you were in my last talk, you would have heard me talk about how we can use living tissue, so brain cells, to be able to do compute. And what I'm going to talk to you today about is how we can do the other side of that. So instead of using the actual neurons themselves, how we can use principles of how neurons function or how brains function to develop algorithms that are similar to the brain or similar to clusters of neurons to do AI-like tasks. All right. So I'm going to share a Google Colab. And what I'll do is then I'll just walk through the Google Colab and all of the different code segments so that you can see how this is actually done and then go through a few examples. So what I'm going to talk to you about today is something called reservoir computing. This goes by a few different names that you might hear. For example, echo state networks. They're a particular type of neural network um, that are able to do a very efficient compute. So very efficient classification or prediction of a time series, for example, which is really necessary in our world today when we see that our AI systems are using a lot of energy and a lot of data to be able to be trained. What's also really interesting about reservoir computing is that it mimics the structure or and function of how we believe the brain to be working, very, very loosely, and can be used in a lot of different tasks and can also learn online. So what this means is where with traditional AI algorithms, you need to have a data set and training this data set uh, before you can actually use the algorithm is necessary. With reservoir computing, you can actually take the data as it's coming in, train your network, your reservoir, and then be able to use it instantly. So if I if I sort of start, what I'm going to go through today is how we can use this type of algorithm for time series prediction. So, for example, let's say that we had a weather forecast and you wanted to determine what the weather would be like in the next day, or the rain for one day and the amount of rain the next, or even stock prices, taking the previous price of stock and then determining what it would be the next day. These are the sorts of tasks that are most suitable for reservoir computing, and this just falls under what we call time series prediction. So, what's really great about reservoir computing, the reason why a lot of researchers are moving towards this right now, is that it's really, really simple. Um, you can see in this picture here, we have three parts. We have something called our input layer, we have our reservoir layer, and our output layer. So in a traditional neural network, we have layers, and each of these layers contain neurons that are all connected. Um, but each of these layers have different functions, different what we call activation functions. So think of them as equations that you have to multiply the numbers by. And these things can get very, very complicated as you train the network to do different tasks and have larger and larger networks necessary to do different tasks as well. But with reservoir computing, what's great is that the input layer going into the reservoir is fixed. So what we mean by that is that all of the connections between the data going in and connecting to the reservoir are static from the beginning. And the same is for the reservoir layer itself. All of the connections in between the neurons of the reservoir are static, they're fixed, and they don't change. How is this different from a traditional neural network? Well, a traditional neural network will have a lot of neurons, but those neurons' connections to each other won't be fixed. This is what we are doing when we're training it. We're training the connections between the neurons. But the reason why reservoir computing works is because what we are using is the natural randomness within the reservoir to take our data and increase its dimensionality. So what that kind of means is we have our data in one form, we pass it through the reservoir, and what we actually are doing is we're reading the state of the reservoir, so what each neuron is doing at every point in time, and this gives us lots and lots of numbers through time that we can then take and put into our output layer. And our output layer is actually another classifier, but a very, very simple one. So something like a ridge regression, which is you can think of it as a straight line equation. So you can plot a straight line in between these numbers to be able to say this is our classification, or use this to be able to also do time series prediction. So within our reservoir, there are a very few things that we actually need to set. The first one is the input sides. So this is how much information you're actually going to put into the reservoir itself. Because what we're going to do is use something like stock market data, our input size is just one. So we're simply going to take one number and pass that into our reservoir. So pretty simple. The second thing that we have to set is the reservoir size itself. So this is actually how many neurons are inside of the reservoir. And this is an important metric because the more neurons you put in our reservoir, the more complex the reservoir is, the more states that to read, and it can then take a little bit longer to train. But at the same time, if we have too few neurons in our network, then it will train very quickly, but there might not be enough information, depending on how much data we're putting in, um, to then get a very good readout at the end. And then there are two other things that you may not know or may not have heard of that are very specific to reservoir computing. And this is, first one is called the spectral radius. So what the spectral radius is a number that determines how reactive our neurons are to the data that is coming in. We can set this number from anywhere from 0 upwards. But what we find is that numbers around 1 are usually the best. And this actually comes from neuroscience. So this is a quantity that isn't just in artificial neural networks, but we can actually calculate the spectral radius of real biological neurons in neural networks. And we see that natural neural systems have a value of around 1 when we calculate it. And when this number is more towards 0, the neurons are less reactive, they're more stable. And when this number is greater than 1, they are a lot more reactive. So that when the data comes in, it makes their activity a lot more erratic. And then finally, the last parameter is the leak rate. So what a leak rate means is how much the reservoir remembers the information that has just been put in. So for example, if we set the leak rate to 1, then that means that it's only going to be really focusing on the data that's currently put in. But if we lower this number, so we make it smaller than 1, then it takes in account more data that was previously given to it. So the state of the reservoir before is now also taken into account to help it do a prediction into the future. So really, it's a combination of playing with these 4 parameters and another one, which I'll explain in a moment, that really allows us to be able to do this very, very energy efficient um, classification or time series prediction. And as a comparison, these four parameters plus one more, so it's five, is all that we need to be able to do that versus millions up to billions in neural networks now that we need to train to get similar sorts of classification accuracies. So you can sort of see the order of magnitude in difference in terms of actual computation that needs to be done here. So if we start, first thing we need to do is download these modules, which I've already done. But then the first thing that we're going to actually do is generate some synthetic data. So what sometimes happens is if you try to download data online through Google Colab, there'll be a rate limiting error. So what we're doing here actually is going to simulate some data that will look like stock market data. This is called a random walk. And essentially, what we're doing is setting some random numbers, 10,000 different points, to then be able to create our synthetic stock market data. So, what we're going to do first is set a random seed. What this will allow us to do is generate the exact same plot every single time. Without this line, the plot that you'll generate every single time will be different. But then we'll just do a cumulative sum of all of the random points for these 10,000 points, and then plot this on our plot here. So here you can see that this now is our time series, and it looks just like some stock market data that you'll see if you were to download it from like Yahoo Finance, for example. And then the next thing that we need to do is normalize our data. So you can see right here, if you look on the y-axis, all of the data is between minus 20 and, well, minus 40-ish and 100. But what we want to do is make sure the data is all compressed in between 0 and 1. So what this code will do is normalize our data that we've just got here. So it will be exactly the same plot, but you can now see that the data is now a bit more normalized. It's now in the right range to then go into a neural network. And this is just a standard process that we'll do for any type of neural network, because if you don't, then any excessively large or excessively small numbers might skew how the neuron is, how the network is able to learn. So the next part of this is the actual training and building of the reservoir network. So the way that I've set this up is as a class, because there are several different things within this that will need to be made. Sadly, there aren't many packages online that actually allow you to do this in an easy way. So it is more custom made code that you have to use. But I can see that a lot of researchers are looking into this field right now. So I can see very soon there'll be a lot more off-the-shelf packages available. So if I explain what this class is doing, we make the input size um, of our network, which I said will be 1. And we also set our reservoir size. So we're just setting the different variables here at the beginning in our initialization of our class. You can ask me some questions at the end about classes if you haven't come across these, but this is essentially just setting all of the different parameters to be then put into our class. And then what we have to do is create something called await matrices for our input and our actual reservoir. So if you're familiar with neural networks, what we're actually doing is we're taking matrices, so think of them as 2D grids, to be able to multiply these together. And that allows us to do our calculations just a lot more efficiently. So, like I mentioned before, in reservoir computing, we simply have two matrices, one for our input and then one for the reservoir. And that is what is being done here. And then we have another variable here that allows us to scale the reservoir by the spectral radius that we've set here, which is what this function is doing. And then when we are passing our data through the reservoir, we need to be able to update its state. So we need to be able to say, okay, this data has just come in, multiply it by the value that's currently there, remove some numbers because of the leak rate, and then give us a new state. And this is what this function is doing here. And then we need a final function that will essentially run the whole process with all of our input data. Okay. And then what this will do is just run through that whole process for all of the data and then allow us to see all of that in one time series to then plot. So once we have this, I should probably run this. What we want to do is simulate the reservoir. So we want to actually simulate what these neurons in the reservoir are doing and visualize that. So if we take our input size and then we want to set our reservoir size, so how many neurons are in this reservoir, I'm going to just put in a few different numbers so you can see exactly what I mean by the state. If we start with just 3, for example, and then I run this, you can see that we now have 3 lines, and each of these 3 lines is showing the activity of each of the neurons. So this you can think of as like the electrical activity of a neuron. It's kind of the best analogy. It will produce different numbers as data comes in and it's multiplied, as the leak rate is added, as it interacts with the other neurons that are passing data to it. Because remember, each of the neurons within the reservoir are connected to each other. So as all of the data passes around through time, it changes the actual state of each neuron individually. So you can see that as we increase the number of neurons, so if I make this 30, for example, things start to get a lot more complex. And it's this complexity that allows us to be able to do time series prediction. Because once we take this data and put it into our readout layer, it's actually a lot more what we call sparse. And it allows the readout layer to be able to basically draw a line of best fit through it. I know it doesn't look that way from this plot, but that's because I'm plotting all of the data through time all at once. But then this is where we do the final training. And this is the only thing within a reservoir computing framework that we actually need to train. The final linear regression model that this data is going into. So we take a ridge regression model, which is, like I said, like a line of best fit, if you think about it like that. And we can set our model with a regularization parameter. So it kind of makes sure that it doesn't overfit. And then we can take the states of the reservoir versus what it should be and fit our line to that and make our predictions. And then this line does our plotting. And then we finally do a calculation to compare our prediction with the actual value that it should be. And what we're using for that is the mean squared error. So the mean squared error basically is one of many different types of metric that we can use to evaluate how how good the performance of our network is. So if I run this, what you can see is that this network has performed very, very well because the actual is in blue and the red is in predicted, and the is our predicted, so what the reservoir has actually come out with. And you can see that it pretty much perfectly overlaps this uh, this the actual plot. There are only a very few points where it doesn't, but that's actually the power of reservoir computing. It's perfect for time series prediction. It's able to do this with very, very little compute resources. I mean, we were able to do this on Google Colab without having to use a GPU at all. And if you were to use something like a deep neural network, you definitely need to use a GPU. If we look at the mean squared error, we have a value of 0.001, and that is quite good because the closer to zero you are, the better it is. So that is pretty much reservoir computing. And like I said, it is a very simple and straightforward algorithm to use. You set up the reservoir, you pass the data in, you simulate, and then you compare the prediction versus the actual. But what I want to do here is just show you actually how the different parameters impact the performance of your algorithm. So here we have a few different things that we can change. Like I said, we want to be able to change the number of neurons. So that's what this first one is. We want to be able to change the spectral radius, the leak rate, and we're also able to change this the regularization of that readout layer. So the only thing that we're training, there's one parameter within that we can also train. And this other dial is just making the data a little bit harder to model. So you can see here we kind of add noise to the data to make it a little bit more jagged. So if I choose a alpha, so a regularization in the readout layer that's too high, you can see that our line is now not following the real data at all. So this is why training that readout layer is really, really important, because then it really doesn't matter how big your reservoir is, how you really change the spectral radius or the leak rate. It doesn't really have a good accuracy. I mean, this is not that bad, but you can see here at the very end, it's really not being able to capture um, this pattern here or any of these peaks. So if we bring down this alpha into a range that's better, then we see that the prediction actually starts to get better as well. And if we bring down the number of neurons and we bring up the spectral radius, you can start to see actually how each of these different parameters impacts the performance. So it's very, very, one of the things that you have to do is pick which ones of these you want to stick with. So let's say we're going to stick with a reservoir that has 100 neurons. What you have to then do is probably do something called a parameter search around these other parameters to be able to know which one is the best. Like I said, the spectral radius around 1 is usually ideal. So this is kind of given. You don't have to do too much searching around parameters for that. But things like the leak rate and then also the alpha for your readout layer, these are things that you're going to want to play around with a little bit to be able to get the right sort of values to get a good classification. And you can see here that having the alpha as low as possible is actually the best thing for this particular network. because as you increase that, it doesn't perform very well. Right. So that is my little workshop on reservoir computing. I know it was kind of a lot to go through in a short period of time, but this is what I think is going to be one of the most used algorithms in the next years for time series prediction, purely because it has a lot of applications. Um, it can be used in a lot of applications that allow for compute to be moved away from large data centers and onto what we call edge devices. So, for example, this sort of algorithm would be possible to run on your phone. You could run it on any kind of hardware that doesn't have a large GPU, and that will bring AI or you know this kind of predictive computing a lot closer to where the data is. And I mean, that's good for energy consumption, good for data consumption as well. Right. Thank you.
Thank you so much, Robert, for your presentation. Now we're moving forward with our Q&As from our audiences, and they're really inspired by your presentation, so that we have quite a few. One of the questions is, what is exactly reservoir?
Reservoir.
Yeah, reservoir. Yeah.
So the reservoir is a collection of neurons, and they're all connected to each other. So an interesting analogy is the brain. The brain can be considered as a reservoir. We have lots of neurons all around, and they're all connected to each other. I mean, they're not all connected to each other, but there is a structure, and that structure is fixed. And that's the main thing to think about here. If you think drawing a lot of dots and then just drawing lines in between all of them to connect them together. This is what a reservoir is.
Thank you so much for your answer. We're moving to the next question. Where we can train to do such experiments?
Yeah, so like I mentioned, there's sadly not that many different Python packages that you can just download and use. But I can share this script and you can play around with it. I mean, in general, there's ChatGPT. There's a lot of different chatbots that you can use to help you develop these sorts of things. And then, like I did here with Google Colab, you can simulate data. You can get data from other places to be able to um, do pretty much anything. So, classification and time series prediction are the best things to use reservoir computing for.
Thank you so much. Another question is, what are the noise level and ridge alpha variables are for?
Yeah. So in my example, the noise level was just so the data that it was trying to model would be a little bit harder to model. So because it's not real world data, I just wanted to add a little bit of noise. So this is a concept in computer science. Adding noise just means adding a little bit of randomness to your data. And the ridge alpha. So I remember saying there's three parts to your reservoir computing framework: the input, the reservoir itself, and then the readout layer or the output layer. The output layer is a classifier in itself that needs to be tuned to be able to interpret the state of the reservoir, and that's what that is.
Thank you so much. Another question is, what made you interested in AI in the first place?
Yeah, so what interested me in AI, it's actually quite interesting in itself. So I was originally doing my undergraduate in biomedical science, and I was doing a project in drug discovery. So uh, actual developing chemicals that could interact with neurons. And I started to look into how that software actually worked, and I was reading about this idea of training sets and test sets, and I found that just really interesting that how you could use data and learn from it to then do biology. And looking into that further, I just thought, yeah, this is something I want to do after learning that AI is really just maths. So I think that's kind of what really drove me towards it.
Thank you so much. Moving on to the next question. If each neuron is connected and data passes through, does it also change the positions of the neuron?
No, no. So everything about the reservoir and the input is completely fixed. The neurons are static, and the only thing that changes about the neurons is their state. So you can think about that as what number uh, it contains.
Perfect. Thank you. What other resources do you suggest to explore further to understand the basics of this emerging technology? Any other learning courses you suggest?
Yeah. So reservoir computing itself is quite new in terms of its use. It's not new in terms of the ideas, but they've been largely just confined to academic research. Sadly, there aren't any courses that I've seen that incorporate it. Um, I think I think if you're interested in this as a concept, um, just looking at what's available online, looking at other things like liquid state networks and echo state networks would be good. Um, but like I say, a lot of it is academic papers. So what I always, do recommend is taking these papers and putting them through a language model and getting them to summarize and simplify and explain how what they're doing functions. But the beauty of reservoir computing is that it's there isn't a lot to do. It's set these parameters and then pass data through it. Um, the only kind of hard part would be the optimization of the parameters, so choosing what numbers to actually set those at. So I wouldn't even say that doing that would be hard.
Thank you so much. Since biocomputing is still new, what are the ways to create awareness about it, as not a lot of people know about biocomputing?
I mean, the best way is really things like this. So talks, um, and really just talking about it. I don't really know if there's any other way right now because it's quite early, so there isn't much to show in terms of real world use cases just yet. Um, I can see that there will be some real world use cases definitely in the next few years, but they won't be super functional if that makes sense. So, for example, I previously showed that a group was able to play Pong with these neurons. But playing Pong isn't necessarily something that is going to be super useful for everyone and make it something that everyone talks about. It's just sort of something that's quite cool. Um, so we'll definitely see a lot of that in the near future, which will get people talking. And I think that's probably where it's going to be for the time being.
Thank you so much. How do you ensure the security and privacy of neutral data in BCI systems?
Okay. So that's actually a really interesting question. Because right now there's a lot of talk about, okay, should we integrate blockchain systems? Because blockchain is inherently cryptographic. So you put the data in, you hash it, so you convert it into a string of numbers that can you can't read. So this is one way of making sure that neural data can be um, secure. And other ways are things like federated learning. So because BCI systems have to have an algorithm attached to them to decode the brain signal, instead of taking that brain signal and then putting it into the cloud, you can actually do all of the compute locally, so right next to the person on a device, and all of the learning is done there. So no data actually moves from the BCI to any other place. The learning happens where the data is collected, and then if there's a model that needs to be trained and improved, the parameters from the local model get put into the cloud. So no data is actually transferred.
Thank you so much for your answer. We're moving to our next question. What are the different data types that will be used in creating a chatbot and how it can be used?
So it's interesting because with chatbots, if you think about them as what they're made up of, rather than uh, okay, these are things that I can talk to. So they're made of transformers. Um, they can take in a lot of different types of data. It doesn't have to be text. I've seen ChatGPT like algorithms be used with biological data. So if you think of that, you can pretty much turn any data into a string. Um, so mostly you're looking at text, so letters and numbers. But if you can turn your data into letters and numbers, that's in a unique way, then it can pretty much be anything. So, for example, you can represent chemicals as what are called smiles strings, so just letters, and you can then put that into a chatbot-like device to be able to do generation.
Could biocomputing play a role in making BCIs more accessible and affordable?
Yes, yes. So that's actually what I work on. I work on using neuromorphic algorithms, so algorithms that like reservoir computing and echo state networks to make sure that the compute is a lot more efficient and it can be on device. Um, Making them more accessible and affordable isn't just down to the algorithms though, because there's hardware. You have to be able to get the signal from a person's brain to be able to classify it, to be able to get it to do something. So there's a little bit more than just the algorithms themselves. But if you are using algorithms that don't require um, very energy intensive hardware, then that's one step in the right direction.
Thank you so much. Which package can be used for this real world data?
Yeah, so if you want to um, do work like this, but then to incorporate real world data, then you can use Yahoo Finance. That's one. You can then take actual stock market data to be able to feed that in as a time series. Another one that's quite good is Google Trends. So you can get the the historical usage of any word or phrase from Google as a time series to be able to do a similar sort of time series prediction. Um, there are a few others. Let me think. So those two are good because they are just downloadable through a pip install, so you can just write some code and then use them right away. There are a few others that, so I think the Federal Reserve has, like the American Federal Reserve has a package itself that allows you to download data, but you need an API key, which you probably can get. And yeah, those are probably the good examples to start with.
What breakthroughs are needed for numerographic computing to become mainstream, and how do you see its roles evolving in AI over the next decade?
Yeah, so I mean, we're seeing quite a few breakthroughs in neuromorphic computing right now. The the I think what what we're missing are more accurate models of neurons. I think that is one of the major um, bottlenecks that we have right now because we understand where these are useful, but being able to simulate a neuron digitally accurately, we're still not entirely there yet. We have a lot of different ways of doing that, but that's the problem. We have lots of different ways of simulating neurons. So which one is the best? And then also converting data into a data type that is compatible with different neuromorphic algorithms. So this one that I showed you is perfect for using data as it is. We can just put the data in as numbers. However, there are other types of algorithms that, for example, spiking neural networks, that work by mimicking the actual functioning of a neuron. So you have actual spikes in the same way neurons have spikes, meaning that the data needs to be converted into spikes. So doing that in an efficient way for all data types is also a little a bottleneck.
Thank you so much. Can you share some insights on the use cases for leveraging and integrating quantum computing for biocomputing?
Yeah, so quantum computing and biocomputing can come together in the sense of using reservoirs. So if you were to take a neural organoid, so a three-dimensional culture of neurons, this could be considered a reservoir. So you can do the exact same sort of things that I was talking about here by reading the states of the organoid, so the spikes. And also you can do the very similar thing with a quantum reservoir. So reading the state of the quantum reservoir and the neural reservoir themselves, these two things can in some way be combined. So what I've seen being done in literature, not with quantum and neural reservoirs, but with just um, reservoirs themselves, is by connecting them. So you pass data through one, take the data out of one and pass it through the other, and that actually increases the classification accuracy overall, because what you're doing is you're putting data in, making it more readable, and then you're putting that data into another reservoir and making it even more readable. So if you were to do that with a quantum reservoir and then a neural reservoir, or maybe the other way around, then you get the same sort of effect.
Thank you so much. Moving to our next question. How does biocomputing help tackle STEM problems?
STEM problems. So I'm assuming STEM as in science, technology. Ah,
Yeah.
so I mean, what's really interesting about biocomputing is that it combines two fields. It combines biology, it combines computer science. I mean, there's a lot of math in that as well because you need to understand how a neuron or any kind of biological system functions, but then be able to put that in a mathematical way. So I think because of the cool factor of it as well, it can really draw people into wanting to maybe learn the math behind it and wanting to and seeing that okay, there's a little bit more to computer science because I can do biology with it, and there's a little bit more to biology because I can actually do computing with it too.
Thank you so much. Due to our time limitations, I'm just going to ask you one more question from our audiences. Numero Neurographic chips are often inspired by the human brain. How close are we to replicating true brain like computation, and what are the biggest challenges?
Yeah, so in terms of how close are we to replicating the human brain? We're not very close to replicating the human brain because it's so large and um, we, for example, we've only managed to really image and replicate a small section of the mouse brain. There's a lot of initiatives looking to do exactly this, though. Whole brain emulation is a field of itself. Um, and what they tend to do in this field is take electron microscopy slices of neural tissue and then model this and try and build a bigger picture from these smaller starting points. Um, Other people have tried to replicate the brain computationally. So rather than going from the individual neurons, try to computationally model different functions. And even with that, again, we haven't managed to do every function of the brain. There are some groups that have managed to do um, modeling the speech. So how the speech part of the brain then allows our tongue and mouth to move and produce sound. There are other groups that have modeled how the motor cortex is able to produce muscle movements, individual muscle movements in the hand, not the full body. So there are kind of two different ways of looking at it, but we're still very, very far away from replicating the whole brain. Um, yeah.
Thank you so much. Even though we have time limitations, our audiences are actually so inspired and asking so many questions. So I'm just gonna have one more question for you.
Okay.
What are some leading companies in the biocomputing in neuromorphic chips?
Yeah, so in terms of biocomputing, you have Cortical Labs, you have um, Final Spark. These are two of the biggest ones. In terms of neuromorphic chips, there's a company called Rain AI, and they're probably the biggest one. But also Intel. Intel has a lot of research into making neuromorphic chips as well, and I'm sure there will be a lot more popping up. There's a lot of this is still in academic research. Um, there aren't that many neuromorphic chips on the market, but they're very close to being on the market.
I've checked it with my team, and we see that our participants are really engaging. So we're gonna still continue with our Q&A.
Okay.
Um, can nomographic computing aid the formation of cells?
No, so stem cells and neuromorphic computing are a little bit too far apart to be able to really help each other, at least physically. I mean, AI seems to be quite useful in all areas. Potentially, you can use a neuromorphic chip or neuromorphic algorithm to help design a protocol to then help how you design your stem cells or grow your stem cells. Um, but nothing direct that I can see right now.
Thank you so much. Another question is, how about Elon Musk's Neuralink? It's different by
So Neuralink, what they do is they have created a brain computer interface that's implanted into the brain, and it's implanted using wires. So the way that their system is different from the stuff that I do, for example, is that it's what we call invasive. So you have to have a surgery, and well, they don't actually do a surgery, they use a robot to implant it into the person's brain and then inject those wires into the brain to be able to connect to it. The thing that's different about that is from what I do is that I don't have any wires implanted in anyone's brain. They put on a EEG cap and it measures the signal from outside of the brain. There are lots of other companies like Neuralink that have developed invasive brain-computer interfaces. For example, BlackRock Neurotech, they have a system that has electrodes that go into the brain, but that causes damage to it more than what the Neuralink device does. And then you've got others like Synchron that have devices that go into the blood vessels, and then they sort of incorporate into the blood vessel and record from there. So there's kind of a whole array of different devices that you can use to record from the brain.
Thank you so much. How can students and researchers get involved in biocomputing in neuromorphic AI development?
Yeah, so with neuromorphic AI development, there are a lot of open source packages. So I did mention that reservoir computing, there don't seem to be that many. But with just simulating neurons. So, for example, there's Pyn, Pynn. That's a Python-based package that allows you to simulate neurons, and that could be one way of getting into this because if you know Python, then you can get started with this quite easily. There's another called um, SNN Torch, or Spiking Neural Network Torch. If you've heard of PyTorch for training neural networks, then this is another that you can use. And this is for training spiking neural networks. These are networks that work similarly to a um, biological neuron, but like I said, we still don't fully understand how a biological neuron works to be able to efficiently model them. And then there's another called Brian 2. So Brian 2 is another one of these neuron simulators to be able to start to work on how we can build a virtual biological neural networks.
Thank you so much, Robert, for your presentation and answering our participants' questions. We're so happy to have you. Thank you so much.
Thank you.
Thank you so much, everyone, for joining us today. I would like to thank our sponsors, Sage Foundation, and Red Hat for their contributions to this session. So thank you all for joining, and see you tomorrow.